In this video, we are going to study linear differential equations, which is represented as dy by dx plus p into y equals q, where p and q are either constants or functions of x only. And since the order of the differential equation is 1, this is a first order differential equation. For example, dy by dx plus y equals sin x, where p is 1, which is a constant, and q sin x, which is a function of x. Dy by dx plus y upon x equals x square, where p and q both are functions of x. We also can have a linear differential equation of the type dx by dy plus px equals q, where p and q are either constants or functions of y only. For example, dx by dy plus x equals cos y is a linear differential equation where p is 1, which is a constant, and q a function of y. Dx by dy minus x upon y equals 2y, where p is 1 upon y and q 2y, which are functions of y only. This also is a first order linear differential equation. Please note that for dy by dx there is y here, and for dx by dy there is x here. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. We will see how to find solution of linear differential equation dy by dx plus py equals q. Let us name this one. For finding its solution, let us multiply equation 1 by a function of x, say gx, on both sides of this equation. So it becomes gx dy by dx plus gx py equals gx into q. We will choose gx such that the right hand side gx into q is equal to derivative of y into gx. So this becomes gx dy by dx plus gx into py equals, now we will write derivative of y into gx with respect to x. So first function into derivative of second g dash x plus second function gx into derivative of first dy by dx. Now gx dy by dx gets cancelled. Also dividing y from both sides, y gets cancelled. So it is p gx equals g dash x, or p equals g dash x upon gx. Integrating, integral p dx equals integral g dash x upon gx dx. Derivative of denominator gx is in the numerator. Therefore, this integral will be log of denominator, that is log gx to the base e. This logarithmic form in the exponential form as gx equals e raised to integral p dx. Now we will multiply equation 1 by this gx, which is e raised to integral p dx. This gx is known as integrating factor if. We will multiply this equation 2 by the integrating factor e raised to integral p dx. So this will be e integral p dx into dy by dx plus e raised to integral p dx into py equals e raised to integral p dx into q. Now this left hand side is nothing but this d by dx of y into gx. So this will be d by dx of y into, in place of gx, it is integrating factor e raised to p dx equals this q into e raised to p dx. Integrating this will be y into e raised to integral p dx equals integral q into e raised to integral p dx, which is y into integrating factor equals integral q into integrating factor dx. So this is going to be the solution of this linear differential equation. Solve linear differential equation dy by dx plus y upon x equals x square, which can be written as dy by dx plus 1 upon x into y equals x square, where 1 upon x is p and x square q both are functions of x only. So first integrating factor, which is e raised to integral p dx e raised to integral 1 upon x dx equals e raised to log x to base e, which is x. So we get integrating factor x. Now we write the solution as y into integrating factor equals integral q into integrating factor dx plus constant of integration c, which is y into x equals integral x square into x dx plus c, which is xy equals x raised to 4 upon 4 plus c. So this is general solution of this linear differential equation. Solve dy by dx plus sec x into y equals tan x, where x lies between 0 and pi by 2. In this linear differential equation, p is sec x, q is tan x. Integrating factor will be e raised to p dx, e raised to integral sec x dx, e raised to log sec x plus tan x to base e. So the integrating factor will be sec x plus tan x. Now solution will be y into integrating factor sec x plus tan x equals integral q, which is tan x, into integrating factor sec x plus tan x dx plus c, which is integral sec x tan x dx plus integral tan square x dx plus c, which is integral sec x tan x dx plus integral. In place of tan square x, we can write sec square x minus 1 dx plus c, which is integral sec x tan x plus integral. In place of tan square x, we write sec square x minus 1 dx plus c equals integral sec x tan x is sec x plus integral sec square x is tan x minus integral of 1 dx is x plus c. So this is general solution of this linear differential equation. Solve y dx plus x minus y square into dy equals 0. If we try to solve this by dividing throughout by dx, then it will be y plus x minus y square into dy by dx equals 0, which is not in the form dy by dx plus py equals q, which is a standard linear differential equation form. So we will try to write this in dx upon dy form. For that we will divide throughout by dy. So this will be y dx upon dy plus x equals y square. Dividing throughout by y, this will be dx upon dy plus 1 upon y into x equals y. Now this is of the form dx upon dy plus p dash x equals q dash, where p dash and q dash both are functions of y only, or they are constants. Integrating factor is e raised to integral p dash dy, which is e raised to integral 1 upon y dy e raised to log y to base e. So integrating factor is y. Now since this differential equation is of the type dx by dy, our solution will be of the type x into integrating factor equals integral q into integrating factor dy. So this is x into y equals integral y into y dy, which is integral y square dy. It is xy equals y cube upon 3 plus c. Dividing by y, x equals y square upon 3 plus c upon y. So this is general solution of this linear differential equation. Solve dy by dx plus 2y equals sin x. If we compare this equation with dy by dx plus py equals q, where p is either a constant or a function of x and q is a function of x only, which is sin x here. Therefore, this is a linear differential equation. So in this differential equation, p is constant 2 and q function of x sin x. We have seen in order to find the solution of a linear differential equation, we need integrating factor, which is e raised to integral p dx. In this case, it is e raised to integral 2 dx, which is e raised to 2x, and the solution is y into integrating factor is equal to integral q into integrating factor dx plus constant of integration c. We name this 1. So y into if equals integral sin x into e raised to 2x plus c. We name this equation 2. Y into if equals, this is product of two functions, has to be solved by method of integration by parts. We name this integral I and solve it separately. So I equals integral sin x e raised to 2x dx. First function sin x into integral of second. Integral of e raised to 2x is e raised to 2x upon 2 minus integral of derivative of first, derivative of sin x is cos x, into integral of e raised to 2x, which is e raised to 2x upon 2 dx, which is half sin x into e raised to 2x minus, this is product of two functions. So here also we have to use method of integration by parts. So half into first function cos x into integration of e raised to 2x, e raised to 2x upon 2 minus integral of derivative of cos x, which is minus sin x. That makes this minus sin plus sin, and here sin x into integral of e raised to 2x, e raised to 2x upon 2 dx equals half sin x into e raised to 2x minus half into half 1/4 cos x into e raised to 2x. This half multiplied by this half, which is 1 upon 4 integral sin x e raised to 2x dx. So I equals half sin x e raised to 2x minus 1 upon 4 cos x e raised to 2x minus 1 upon 4. Now this integral is nothing but this I. So here minus 1/4 I. This I plus this 1/4 I will be 5 upon 4 I equals, taking 1/4 e raised to 2x a common factor, 1/4 e raised to 2x into this half will become 2 sin x minus cos x. Cancelling this 4 and dividing by this 5, I will be 1 upon 5 e raised to 2x into 2 sin x minus cos x. Now y into if equals I becomes y into e raised to 2x equals 1/5 e raised to 2x into 2 sin x minus cos x plus constant of integration c. So dividing throughout by e raised to 2x, the final solution will be y equals 1/5 2 sin x minus cos x plus e raised to minus 2x into c. So this is the general solution of this differential equation. Solve tan inverse y minus x into dy equals 1 plus y square into dx. If we divide throughout by dx, then it will be tan inverse y minus x dy by dx equals 1 plus y square, which is not of the form dy by dx plus p into y equals q. Therefore, this differential equation is not of the form dy upon dx If we divide throughout by dx, then the equation will be tan inverse y minus x equals 1 plus y squared dx upon dy. Dividing throughout by 1 plus y square, this will be 1 plus y square dx by dy plus x equals tan inverse y. Now dividing throughout by 1 plus y square dx upon dy plus 1 upon 1 plus y square into x equals tan inverse y upon 1 plus y square. Here p dash is this 1 upon 1 plus y square and q dash this tan inverse y upon 1 plus y square. Since this differential equation is of the type dx upon dy, integrating factor will be e raised to p dash dy, which is e raised to integral 1 upon 1 plus y square dy, which is e raised to tan inverse y. So this is integrating factor. Now since this equation is of the type dx upon dy, its solution will be of the type x into integrating factor equals integral q dash into integrating factor dy x into e raised to tan inverse y equals integral tan inverse y upon 1 plus y square into e raised to tan inverse y dy plus c. We will name this integral as I and solve it separately. So we have x into e raised to tan inverse y equals I. We name this equation 1. I is integral tan inverse y upon 1 plus y square into e raised to tan inverse y dy. We will solve this integral by substitution. So we will substitute tan inverse y equals t. Now differentiating 1 upon 1 plus y square dy equals dt. So here we get 1 upon 1 plus y square dy equals this dt, and for this tan inverse y we get t. So therefore this integral gets converted into, for this tan inverse y we write t into e raised to t, and 1 upon 1 plus y square dy equals dt. So the integral has transformed into an integral in t, and since there is a product of two functions, we have to use integration by parts to solve this integral. So this is first function t into integration of second, which is e raised to t minus integral derivative of first, that is derivative of t is 1, into integration of second e raised to t dt, which is t e raised to t minus integration of e raised to t is e raised to t, which equals e raised to t minus 1, which will be I equals e raised to tan inverse y into tan inverse y minus 1. After substituting the value of this I from here, equation 1 becomes x into e raised to tan inverse y equals this e raised to tan inverse y into tan inverse y minus 1 plus c. Now dividing throughout by this e tan inverse y, we get x equals tan inverse y minus 1 plus c into e raised to minus tan inverse y. Please note this minus sign here. So this is going to be the general solution of this linear differential equation. If you like this video, please like, share and subscribe this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.